Hello everyone, in this lecture we will discuss the fundamentals of crystal structures. So let's start defining structure. A structure is defined as an array of atoms specified by a basis with lattices. Now basis is a group of atoms which is repeated. Lattice is a pattern of repeats. Now let's have a look to this arrangement of atoms, assuming that these dark dots are the atoms here. They are called bases in this case here. They are the bases. This one here, this here, and this here. And the lines connected these bases are called lattices. This one is lattice, and this thing here. The whole thing is called structure. So we have here bases, the atoms, the imaginary lines here is the lattice. So repeating this whole thing here is called structure. Assume that we have a one-dimensional system, a linear chain for instance, with two bases. For instance, one here, the green one, like this one here, and the red ones. In this case here, the structure is repeated every, like this one here. Now the bases in this case here, we have two bases, the green one here and the red one here. Consider another one-dimensional system with a different situation, like this one here. Now, as we notice here, the structure is repeated after the green one, if we take this one here, or after this one here. So the repeated structure, this one here, and this is the primitive cell in this case here, which is A. Now in 2-dimension or 3-dimension, the situation is quite different here. The primitive cell is defined by primitive translational vectors A1, A2, and A3. So R in this case here equal to N1, A1 plus N2, A2 plus N3, A3. In such a way, A1 and A2, A3 are primitive vectors. And Ni are arbitrary integers, could be 0 or could be negative. Note here the set of all possible points on the lattice is R. Now, before defining a basis, we must define primitive unit cell. Now consider that we have a cubic system, it's like this one here. Now A1, this is A1, and this is A2, and this is A3. The volume for this box is defined as A1 dot A2 cross A3, the magnitude. A very important note here, there is always one lattice point per primitive cell. So in this case here, if we have 8 atoms right in the corners, this one here, each one of these atoms share with 1/8 of it, because it's a periodic structure, so there's other cubic systems around this one here. So this one here is sharing with 1/8, and we have 8 atoms at the corners, so this is equal to 1. So this is actually primitive cell, and the volume for this cubic system here, it's equal to A1 dot A2 cross A3, or equal to A2 dot A3 cross A1, or equal to A3 dot A1 cross A2, this one here. One more note here, or the bases associated with primitive lattice cell is called primitive bases. Let's define Bravais lattice. Now remember, lattices are characterized by their symmetry properties, which means one can always construct a unit cell with the same symmetries as the lattice. So the unit cell stacked together must fill all the space without leaving any gaps. Now to achieve this condition, you will notice that no Bravais lattice exists with 5-fold symmetry, only with 2, 3, 4, and 6 symmetries. To achieve this condition, notice that no Bravais lattice exists in the 5-fold symmetry, which means you cannot stack pentagons without leaving any gaps between them. So the only folds you will get is 2, 3, 4, and 6 folds. No 5 folds, or even 7 folds. Let's start defining two-dimensional Bravais lattices. In 2 dimension, there are only 5 Bravais lattices. 1. A square lattice. In the square lattice, the primitive vectors A1 and A2 in this case here are the same. This is A1 and this is A2. And the angle theta, it's equal to 90 degrees. So A1 in magnitude, it's equal to A2, and theta equal to 90 degrees. We also notice that the square lattice is invariant under rotation of 2 pi over 4 or 90 degrees. So square lattice is invariant under rotation of 2 pi over 4, in other words 90 degrees. The other type of two-dimensional lattices is hexagonal lattices. The hexagonal lattices looks like this here, this, this in such a way. This is A1 and this is A2 and this is theta here. A1 equal to A2 and theta equal to 120 degrees. The third type of two-dimensional lattices is rectangular lattice. From its name you can tell that A1, in this case is A1, does not equal to A2, but the angle it's equal to 90 degrees. So A1 here does not equal to A2, but theta in this case it's equal to 90 degrees. And you also notice that the rectangular lattice is invariant under 180 degree of rotation. So it's invariant under 180 degree rotation. Now the fourth type of two-dimensional lattices is oblique lattice. In this one here, A1 is A1, this is A1 here, and this is A2. You can tell that A1 does not equal to A2, and the angle it's not equal to 90 degree. So the oblique lattice A1 does not equal to A2, and theta does not equal to 90 degree. The last type of two-dimensional lattices is centered rectangular lattice. From its name you can tell it's a rectangle, this one here. A1 is this one here, A1, and A2 is this one here. So A1 does not equal to A2, and theta in this case does not equal to 90 degree. This is A1, this is A2. Now notice that this one here is not a primitive because it contains two atoms. 1 4 multiplied by 4 atoms plus 1, in total it's equal to 2. So each atom is sharing with 1 4. So 1 4 and times 4 plus this one here, complete one here, it's equal to 2. So this is not primitive cell. Let's summarize what we just discussed so far. A crystal has a primitive cell. So this what we discussed here is crystal has primitive cell. A lattice point is defined in association with the primitive cell, and there is one lattice point per primitive cell, and conventional cell, which means non-primitive cell, contains more than one lattice point. Let's just write them down. Crystals has primitive cell. Lattice point is defined in association with primitive cell, and there's only one lattice point per primitive cell, and conventional cell, which means non-primitive cell, contains more than one lattice point. Another example of primitive cell is Wiener-Seitz cell. To construct Wiener-Seitz cell, follow this procedure. Pick up an atom and make it the central atom, and draw lines with all nearby atoms, like this one here, this one here, this one here, this, and this. Now at the midpoint, and normal to these lines, draw a new line like this one here, another color. Now the area this area here, is called inner side cell, and number of atoms is sharing this inner side cell, it's only one, this one here, the central one. In 3 dimension, there are 14 Bravais lattices, which means the point symmetry groups in 3 dimension require the 14 different lattice types. The first one is triclinic. In triclinic, there is only one type of this lattice. It's a simple one. Now, as we can see in this one here, we have lattice vectors A1, this is A, this is A, and this is B, and this is C. In triclinic, A does not equal to B, not equal to C, and alpha does not equal to beta, does not equal to gamma, and it is called simple triclinic. We only have one type of this lattice. Now, the second one, it's monoclinic. In monoclinic, 2 types of Bravais lattices, a simple one and base-centered. Now we have monoclinic simple. This one here, as you can see, A, B, and C, which means A does not equal to B, not even equal to C, and alpha equal to gamma, which equal to 90 degrees, but not equal to beta. Now the other type of monoclinic is the base-centered, this one here, and in this one here, this base-centered. Right in the middle of the bases, top and bottom here, we have an atom like this one here, and same rule, A1 does not equal to B, does not equal to C, and alpha equal to gamma equal to 90 degrees, but not equal to beta. Orthorhombic, 4 types of Bravais lattices in orthorhombic: the simple one, base-centered, body-centered, and face-centered. Now this is the simple one, and A does not equal to B, not equal to C, but the angles are 90 degrees. So A not equal to B, not equal to C, but alpha equal to beta equal to gamma equal to 90 degrees. Now the simple one, as we can see here, 8 atoms on the corners, and that's it. So the number of atoms in this one here sharing in this cell here, it's equal to 1, because 8 in the corners multiplied by 1/8, it's equal to 1. Now the other type is the base-centered in this one here. Now same rule as this here, but the number of atoms sharing this cell here is as follows: 8 atoms in the corners, each one is sharing 1/8, which means 8 multiplied by 1/8 plus, now this one is sharing half of it, and this one is sharing half of it, so 2 multiplied by half, or in other words, it's equal to 2. The third type of orthorhombic is the body-centered. The body-centered here is there's an atom right in the middle of the structure here, this one here, and the number of atoms sharing this cell here, it's equal to 8 times 1/8, same as before, plus a complete 1 right in here, it's equal to 2. Now the last one is the face-centered, this one, and in this one here, 8 atoms in the corners. Each atom is sharing 1 8, and plus in the middle of 6 faces of the cube there is an atom. This atom is sharing with this cell here and the next one. So 6 times half here. So in total, the number of atoms sharing this cell here, it's equal to 4. Now another type of three-dimensional Bravais lattices is hexagonal structure. In hexagonal structure, A1 it's equal to A2. This is A1, this is A2. So A1 equal to A2, but it's not equal to C, and alpha is equal to beta, which equal to 90 degrees, but not equal to gamma. In this case, it's equal to 120 degrees. And this is the hexagonal lattice. Triagonal. Only one type of triagonal structure is this one here, and A1 equal to A2 equal to A3, but alpha equal to beta equal to gamma, but not equal to 90 degree, and they all less than 120. It's alpha, beta, and gamma, and it's less than 120 degrees. Tetragonal. Two types of tetragonal lattices. It's simple tetragonal and body-centered tetragonal. Now the simple tetragonal, as you can see here, A1 equal to A2 but not equal to C, and alpha equal to beta equal to gamma equal to 90 degree. This is simple, this one here. Now it's called simple because we have here 8 atoms right in the corners, as we can see here, this one here, and each atom is sharing with 1 8. So 8 times 1 over 8 equal to 1. Now the body centered, in the middle of the cell here we can see a complete atom. Here, this one here, it's called body centered, and same rule as in this one here. This is simple tetragonal. You can see here A, this is A, this one, and this is A2, and they are the same, and this is C, this one here. And the most important crystals is the cubic one, and we will focus on these cubic systems. Cubic crystals are 3 types. This cubic. Now it's simple cubic, body centered cubic, and face centered cubic. Now this is simple cubic crystal, as we can see here. A1 it's equal to A2, it's equal to A3. It's a cubic, by the way, and the angles alpha, beta, gamma, it's equal to 90 degree. Now the body centered cubic, right, this one here, there is same as simple, but there is another atom. It's in the middle of the cubic crystal. Now in the face centered cubic, As we all know that the cube has 6 faces. There's an atom in the middle of each face of the cube. To summarize what we discussed so far, we mentioned that we have 14 Bravais lattices. Let's see. Triclinic, 1, monoclinic, 2 types, orthorhombic, 4 types, hexagonal, 1, triagonal, another one, tetragonal, two, and the cubic, 3. In total, 1 plus 2 plus 4 plus 1 plus 1 plus 2 plus 3, it's equal to 14 Bravais lattices in 3 dimensions. As we mentioned before, we will focus on the cubic system. Now let's start with the simple cubic. In simple cubic, the primitive cell is defined by the primitive translational vectors AX, AY, and AZ, or A1, A2, or 3, and there is only one lattice point. Now this is simple cubic lattice, as you can see this one here. All sides of this simple lattice have length A, because it's a cube. This is A, and the depth is A as well. An example of a simple cubic crystal is polonium. In polonium, as a special case here, A equal to 3.34 angstrom. This is for lattice parameter for polonium. The number of atoms per primitive cell, it's equal to 1. Now 8 atoms, we have here 8 atoms in the corners of the cube. That's 1, 2, 3, 4, 5, 6, 7, 8, and this one here, it's the same as the yellow one, but just we make it blue just to make it as the origin. Now each atom of these is sharing 1/8, so 1/8 multiplied by 8, it's equal to 1. So the primitive cell in simple cubic contain just one atom. Now let's name this one x-axis. Just take like this one here. Now let's name this one x-axis and name this one z-axis and this one here y-axis. The number of first nearest neighbors, or the coordination number, is, let's see, assuming that the blue one here is the origin. Now the first nearest neighbors is this one here, it's like this here, and there's another one, it's somewhere here, and this one here, and there's another one on the y-axis, it's right here, and this one here, and there's another one located somewhere here. So 1, 2, 3, 4, 5, 6. So the coordination number, or first nearest neighbors, for the simple cubic crystal is 6. So nearest first neighbor equal to 6. Now let's find second nearest neighbor. Now in the second nearest neighbor, let's just stop it here. Now in the second nearest neighbor, let's assume this is the x-axis, and as we mentioned, this is the first nearest neighbor. Now the second nearest neighbors, it's in the diagonal, this one here, and another one should be somewhere here, and another one should be somewhere here, and another one should be somewhere here. So in the xy plane, this xy plane, we have 4 atoms, second nearest neighbors. Now when we rotate this one here, in the zy plane, this is z and this is y right here. Now we have second nearest neighbor is this one here, and there is another one, this one here, another one here, another one here. So in the yz plane, another 4 second nearest neighbors. Now the third part is in the xz plane, this one right here. Again, 1, 2, 3, 4. Now let's summarize what we mentioned before. In the xy plane, we have 4 atoms, 4 second nearest neighbors, and in the yz plane, we have 4 second nearest neighbor, and in the xz plane, another 4 second nearest neighbors. 4 plus 4 plus 4, so it's equal to 12. So the second nearest neighbors in simple cubic crystal is equal to 12. Now the volume of the conventional cell of simple cubic crystal, it's equal to A cube, and the volume for primitive cell, again, it's equal to A cube, or A1 dot A2 cross A3, and remember A1 in this case it's equal to AX hat, A2 AY hat, and A3 equal to AZ hat. Now let's find the relation between the radius and distance A. As we can see here, atoms, this atom here is in contact with this one, and it's in contact with this one, and in contact with this one, and this one as well. So A in this case, this is A, this is A, and this is R, and this is R. In this case, A it's equal to 2R, or in other words, R equal to A over 2. Now let's define packing fraction. Packing fraction is defined as the fraction of space filled by touching spheres at each lattice point. So it's defined as n multiplied by the volume of this sphere divided by A cube. N in this case for simple cubic crystal is equal to 1 equal to 1/8 times 8 equal to 1. The number of atoms in the primitive cell here, it's equal to 1. So the packing fraction equal to n, in this case it's 1, 4 over 3 pi. Now r, it's equal to a over 2 in this one here. So a over 2 cube divided by a cube. You simplify this one here, you will get the packing fraction for simple cubic crystal equal to pi over 6 or 0.524. Now the other type of cubic crystals is BCC, or body-centered cubic crystals. Now in BCC, as we can see here, it's similar to the simple cubic, 8 atoms on the corners of a cube, and there is an atom in the center of this cube, this one here, the red one. And notice that all atoms should be the same type. We color the middle atom here with red in order to visualize the structure well. Now let's find the first nearest neighbor for the BCC structure. See here, if we pick up the one in the middle here, 4 atoms on the top, 1, 2, 3, 4, and 4 atoms in the bottom, 1, 2, 3, 4. So the coordination number, or the first nearest neighbors for BCC crystal, is equal to 8. Now the second nearest neighbors, let's just pick up this, the blue one here is the origin. So 1, and there's another one right here, and 3, and another one right here, 4, and this is 1 and 1 here, so 6. So the first nearest neighbors in BCC crystal is equal to 8. Now the second nearest neighbor in BCC, it's equal to 6. By the way, there is no need to go further than 2, because the third nearest neighbor will be 8 and the fourth one will be 6, and so on and so on. So we will need actually just the first and second nearest neighbor. Now the volume of the conventional cell, this conventional, it's equal to a cube, and remember it's a cube with sides a, this is a, and this is a, and this is a. Now the volume of the primitive cell, in this case it's different than the simple cubic, because the volume for a primitive cell, it's equal to a1 dot a2 cross a3, this one here, and a1, it's equal to half a x hat plus y hat minus z hat, a2 equal to half a minus x hat plus y hat plus z hat, and a3, it's equal to half a x hat minus y hat plus z hat. When you just multiply this and this using this rule here, you will find the volume of the primitive cell here, it's equal to a cube over 2. Now the packing fraction for the body-centered cubic packing fraction, we will follow the same rule as before. It's equal to the number of atoms that build this cell here, it's equal to 8 atoms in the corners, each one will share with 1/8. Now 8 atoms, 1/8, plus 1 complete atom in the middle of the cube. So the number of atoms used to build this cell here, it's equal to 2. So the packing fraction, it's equal to 2 times the volume of the atom or this sphere 4 over 3 pi r cube divided by a cube. Now the question is, what is the relation between r and a? Remember, in the simple cubic, a over 2 it's equal to r. This one here, it's different. Now look, this atom is not in contact with this one here, not even with this, not even with this, not even with this. This atom is in contact with the red one, and the red one in contact with this one. Let's just have another visual here. Let's just take it. Now again, this atom is not in contact with this one, so there is no direct relation between r and a in this one using this one here, not even this one or this one or this one. But the green atom is in contact with the red atom, and it's in contact with the blue one, and the green, red and blue, it's the diagonal of the cube, and the diagonal of the cube, in this case this one, just and the diagonal of the cube, it's equal to 4r, because this green one will share with r, the red one is sharing with 2r, and the blue one is sharing with 1r. So 4r, it's equal to the diagonal of this cube, is just the cube here, now we are talking about this atom, the back one, with the middle one and the front one. So the diagonal of this one is the diagonal, okay, this diagonal, and let's find this diagonal of the base here. So the base here, it's a. Now this one here, it's square root of 2a. Now this part here, it's equal to a. Now we have right angle triangle, this one like this. This is the base, this one here, it's square root of 2a, and the height, it's equal to a, and this one here, it's equal to 4r. 4r equal to square root of a square plus 2a square, or 4r, it's equal to a square root of 3, r equal to square root of 3 over 4a. Now the packing fraction equal to, as we mentioned, 2 atoms sharing times 4 over 3 pi r, in this case it's equal to square root of 3 over 4 a cube divided by a cube, and the packing fraction for BCC structure, it's equal to 0.680. Now the third part of cubic crystals is face-centered cubit. Now this one here, in the middle of each face of the cube side, there is an atom like this one here, the red ones, and again all atoms have to be the same type. This one here, like this one here. Now let's pick up an atom and make it as the origin. Now the blue one here is the origin, as you can see, this one here. Now let's find out what is the coordination number, or the first nearest neighbors in face-centered cubic system. Assuming that this is X, and this is Y, and this is Z. Now, on X, on this face here, the first nearest neighbor to this blue one is this one right here. And another one should be right here. Another one should be here. And another one should be here. So in the XY plane, 4 atoms is nearest to this one here. Now, in the XZ plane, we have this one here, another one, and this one, and this one. And the last one in the YZ plane, so this is Z and this is Y. We have this one here, this one, this one, this one. And in total, in the XY plane, we have 4 atoms. In the XZ plane, we have another 4 atoms. And in the YZ plane, another 4. So in total, 12 first nearest neighbors. It's similar to the simple cubic second nearest neighbor, but this one here in the FCC, its first nearest neighbor is equal to 12. The coordination number, or the first nearest neighbor in the FCC structure, is 12 atoms. Let's find out the second nearest neighbor. In this case here, if this is X, and this is Z, and this is Y, in this case, we have this one here. It's not in the diagonal, it's this one, and there's another one on the other side of the Z-axis, and one in the X-axis, and the other one in the negative Z-axis, one here and one here. So the second nearest neighbor in FCC structure is equal to 6. Now, first nearest neighbor, or the coordination number, equal to 12. Now the second nearest neighbor equal to 6 for the FCC structure. Now let's find out the volume of the conventional cell. It's cubic system. So if this is A, and this is A, and this is A as well, so in this case it's equal to A cube. And the volume of the primitive cell, it's equal to A1 dot A2 cross A3, in this case here, in such a way A1 equal half A x hat plus y hat, and A2 equal to half A y hat plus z hat, and A3 equal to half A z hat plus x hat. Now you substitute this back in this formula here, you will find the volume of the primitive cell in FCC structure, it's equal to A cube over 4. Now let's find out the number of atoms used to build this cell right in here. We have 1 atom on each corner of the cube, so we have 8 corners in this case here. Each atom contribute with 1/8. So 8 atoms multiplied by 1 over 8 equal to 1. So 1 atom comes from the corners. Now at the center of each face of the cube we have 1 atom. Now this atom here is sharing with this cell and the next one. So we have 6 multiplied by half. So half of this atom is shared with this cell, and the other half shared with the next one, so it's equal to 3. In total, the number of atoms used to build this cell here, it's equal to 1 plus 3, which equal to 4. Now let's find the relation between the lattice parameter and the radius of the sphere. This is the radius of the sphere right here. This is the radius of the sphere, and this is A from center to center. And this is A as well. Now to find the relation, pay attention here that this atom, it's not in contact with this one here, and this one, it's not in contact with this, not even this one here. The only atoms in contact, it's in the diagonal of the face of the cube, which is this one here. So R is shared from this one here, 2R from this one here, and 1R from this one here is the diagonal here. So 4 R's equal. Now this is right angle triangle with length equal to A and height equal to A. In this case, it's equal to this one here, A square plus A square, or 4R equal to square root of 2A in such a way R equal to square root of 2 over 4A. One last thing here, the packing fraction for FCC structure, it's equal to N, and in this case it's 4, we just calculate this one here, the number of atoms used to build this cell, times the volume of this sphere, 4 over 3 pi R cube over A cube, and R in this case here, it's equal to this one right here. So the packing fraction equal to 4 over 3 pi square root of 2 over 4 A cube over A cube. You do the math, you will find that the packing fraction for FCC structure it's 0.74, and remember this is the maximum packing fraction you can get. Now let's define index system for crystal planes. The orientation of a crystal plane is determined by 3 points in the plane. Note here. We actually need this index system to study the X-ray diffraction for the crystal. Later on we will see how is that related with the X-ray diffraction. The rules to find the index system for crystals is very simple. First, find intercept on the axis in terms of lattice constant A1, A2, and A3. Take the reciprocal of these numbers and then reduce to 3 integers having the same ratio. Normally, the smallest 3 integers. Now, the result is closed in parentheses like HKL is called the index of plane. Let's just summarize the steps. Now, for example, if we have a plane which intercept with the axes at 2, 3, 2. Take the reciprocal for these 3 integers and it will be 1 over 2, 1 over 3, 1 over 2. Now find the least common factor, make them integer. In this case, you multiply this with 6. By multiplying this with 6, you will get 3, 2, 3. Note, if the intercept is negative, in this case here, you just place a bar at the top of the number. So rather than writing like this, 3, 2, 3, you write them like -3 at the top in this case here. These are called Miller indices. So it's called Miller indices. Example, in these three cases, this case number 2 and this case number 3, this one here, find the Miller indices for the highlighted planes. In this case, let's find the intercept. So if this is the x-axis here, so this plane will never intercept with the x-axis, which means they will meet at the infinity. So the intercept for case number 1 here is infinity. In the y-axis, it intercepts with the y-axis at 1. And again, this plane will never intercept with the z-axis, so it's infinity. Take the reciprocals, it's 0, 1, 0. No need to multiply with anything, it's just ready. This is the Miller indices for this plane. Now consider the other case, case number 2, this one here. This plane intercept with the x-axis, this is x, at 1, and intercept with the y-axis, this is y, at 1, and never intercept with the z-axis, which means infinity. Other words, take the reciprocal, it will be 1, 1, 0. Now let's consider the third case here. This plane intercept with the x-axis at 1, in the y-axis at 1, but in the z-axis at -1. Take the reciprocal, it will be 1, 1, and again we just place the minus sign at the top of the number. It's like -1. Now let's have some real examples in cubic systems. The first one is cesium chloride. As an example for the cubic systems is cesium chloride. Cesium chloride is a type of a unit cell that is commonly mistaken as a body-centered cubic, but in reality it's a simple cubic, because the one right in the middle here, it's different than the one on in the corners. This one here is cesium, and the white one is chloride. So this is actually simple cubic, not BCC. Although it looks like a BCC, this one here, but it's a simple cubic. As we mentioned before, atoms has to be in the same type, not like this one here. And we have here two atoms, chloride in the corner, and the one in the right in the middle, it's cesium. So this one is simple cubic crystal. Now the basis position, let's say if we can, this one here is cesium. The basis position cesium, here's one here, is half, 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 and the chloride ion is 0, 0, 0. So this one here, let's take this one here, is the chloride 0, 0, 0, and this one here half, half, half. Another example is sodium chloride, NaCl. This one here. So the green one is chloride and the blue one is the sodium. This is sodium and this chloride. Sodium chloride is an FCC structure with atom positions chloride, this one here, the position is the origin, so 0, 0, 0, and the other one, which is this one here, it's in the X and z plane, so it's equal to half 0 half, and this one here it's in the yz plane 0 half half, and the last one, this one here, it's in the xy plane half half 0. Sodium, on the other hand, the position for the original one, it's half half half. Once you shift the sodium chloride on the x-axis only half, you will get 0. And remember, 1 is a complete lattice, it means 0. So 1 0 1 0 and so on. So 0 in this case here, half half, or half, you shift it in the y-axis, 0 half and half half 0. So this one here, the location for this sodium here, it's half half half. You shift this sodium in the x-axis, you will get this one here, and you shift in the y-axis and shift in the z-axis, you will get the so for sodium, as we mentioned before, half half half, or 0 half half, or half 0 half, or half half 0. Another example is hexagonal closed pack structure. Now in hexagonal structure we have two types actually. So we have a group of atoms, let's name them this one A here, and another atom placed on the top of layer A, this is named B, exactly like this one here. So this is A and this is B. Now the third layer, we have two choices here. If the third layer placed on top of the second one, and again exactly at the top of A, so the third layer will be A in this case here. So this is A, and this is B, and this is A. So the sequence will be A, B, A, B, A, B, etc. In this case, this is called hexagonal closed pack structure. But if the third layer shifted not on top of A, in this case, the sequence will be A, B, C, A, B, C, and so on. This will be face-centered cubic crystal. Let's see how that looks like. Now this sequence here is A, B, this is the blue one, B, and this is C. It's not on top of A. In this case, the sequence is A, B, C, A, B, C, and again, as we mentioned before, it's FCC structure. And since it's FCC structure, the packing fraction for this structure, it's the same as FCC, it's 0.74. One of the most important structures is diamond structure. Now this is a diamond structure, this one here, and you might all know that diamond is a carbon structure. The atoms here is carbon, all of them is carbon. So diamond, it looks like two FCC merged in each other. And the number of atoms used to build diamond, it's 8 atoms. It's not 4 like FCC. So 8 atoms. Now, by looking at the structure here, we have 8 atoms on the corners and we have in the middle of the face here, we have one atom here. Let's have this one here. Now we have here 8 atoms in the corners. This one here in the this face here, and this one here located 1/4 a distance from the this face. Now this atom here is located 1/4 A, and again it's 1/4 A. So this atom here is, let's say this is atom 0, 0, 0. This one will be half 0, and this one here will be 1/4 the position, this one here. Let's find out the basis for this FCC structure. It's 0, 0, 0, and 1/4, 1/4, 1/4. Let's calculate the packing fraction for diamond. Diamond packing fraction. Now, if we just take a piece of this diamond structure, take the base atoms like this one here, this and this. Now the distance here, it's half A, and the distance here, it's half A as well. Now the other one, the one on the top, the green one here, located a distance 1/4 from the middle of the square. So the distance here is 1/4 A. Now this blue atom here, it's in contact with the green one here, so 2R in this case, this is 2R, equal. Now this diagonal here. Now the base of this triangle, it's this one here. Now if this is half A and this is half A, this will be, let's name it X here, equal to half A square plus half A square. In other words, it's equal to half A square root of 2. Now we actually need half of it, so it's equal to 1/4 A square root of 2. So the distance here, it's equal to 1/4 A square root of 2, and this one here is 1/4 A. Now 2R, actually it's equal to 1/4 A square plus 1/4 A square root of 2 square, or in other words 1/4 square root of 3 is equal to 2R. R in this case, it's equal to A/8 square root of 3. Now to find the packing fraction, remember, N in this case, it's 2 FCC merged together, so it's 8 4/3 pi. R in this case is square root of 3 A/8 divided by A cube, and this cube as well, and the answer is 0.34.